Alright, it's been a little while since I posted a video, so I just wanted to show you what I've been up to the last few days here. One of the feedbacks that I got from the open beta period was that people really wanted faster grid charging. And on the RevC PCB, which this is not, is a RevB, but the circuit didn't change for RevC. This circuit right here is what switches in the grid charger. So just this portion on the top that you can see right there. And it's basically an isolation stage and then a triac driver and a fuse, of course. And then this is a feedback sensor, so we can tell what voltage is present. But anyway, on the RevC, the open beta hardware, we found that putting a faster grid charger on there caused that triac to get really hot. So the grid charger that ships by default with LiBCM is this guy right here. It's a 450 milliamp, or I'm using milliamp hours per hour because that's the charge rate, but some people find that confusing. At the end of the day, the units cancel. This is the new grid charger, the maximum power grid charger that LiBCM will natively support, which means like you can just plug it in and it will work. And this will only be on the RevD hardware, so the production hardware. If you have open beta hardware and you want to move up to this bigger grid charger, then you'll need to get the RevD hardware, and I'll have an upgrade path for that. It'll probably cost like $100 or something, and you'll have to send the old PCB in, and then I will send that old PCB to someone who doesn't need this charger. Now this charger is close to $200, and you know I'll be buying them in bulk, which will make them slightly cheaper. I think like $175 if I buy them in bulk. But anyway, the stock LiBCM kit, even in production, is still only going to come with this grid charger here, because this honestly is good for most people. I'm not even going to use this. People just want it, so whatever. This right now takes about 8 hours to charge an empty pack to full. This one will take like an hour and a half maybe. So anyway, that's kind of the difference. That's the change on RevD. It's really the only change on the RevD hardware. I've made some minor ones that don't actually matter. But what I've been doing the last few days then is just finding a heatsink solution that works better. This is the last one that I just tested. This is a MOSFET-based, optically isolated. I use a little, grab a pointer. I have a little photovoltaic isolation right there. So that's literally like a small solar panel with an LED you're driving, and then that's driving the gate on this N-channel MOSFET pair. Now these are really low RDS on MOSFETs. They are rated to 68 milliohms. But what I found, because to me it's an obvious or whatever, of course, but after the fact, MOSFETs actually have a positive temperature coefficient, which means the hotter they get, the faster the rate of increase, because the resistance, the RDS on, increases with temperature. And so this was kind of running away. It's still cooler at room temperature. It's actually quite a bit less power at room temperature, maybe 30% less. But when you get up into when you're actually operating in the car, and the car is 50, 60 degrees Celsius ambient, this starts to be a problem, because when you get this gate, or this MOSFET up to, 125 degrees operating temperature, the RDS on gets pretty large, and the voltage drop across it therefore gets pretty large, and it actually gets worse than the triacs. So this is the last thing I just tested, and honestly I'm glad it didn't work as well, because I've already bought all of the other stuff, whereas I just bought the prototyping of this. So anyway, that was this unit. This handled that large grid charger no problem at room temperature, but it was really struggling. And again, because of that positive temperature coefficient, the hotter it gets, the hotter it will get, basically. It will run away. So what I'm actually going with on the RevD PCB, I just prototyped it on the back here. This is a D2 pack. What is that, TO263, I guess. This is still a triac driver, and I got this beefy surface mount heatsink. Pretty cool, actually, and fairly cheap, to be honest. The first heatsink I tried that was a surface mount, I can't find it right now, but it didn't work very well. Here it is. So here's the two heatsinks compared. This was the first heatsink I was going to use, and this is what I finally ended up using. The price difference on these is only about 3 times. So this is like, I think 50 cents, and this is like $1.50, so something like that. But anyway, this guy's quite a better contender. So I'm doing all of my testing using a board preheater to basically, I have a hole cut in this table here. I've got this preheater so I can set the temperature on it. So I can basically soak the board. So for example, on this test here, I elevate that and I soak the board, and I'm using a thermal imager to see what the temperature is. And I basically am trying to get that to, I think I did testing up to 65 degrees C. Now LiBCM knows the temperature in the car. So if your car temperature, if your battery temperature, or really the air intake into the IMA bay temperature gets too hot, then this won't be able to drive the large grid charger at full power. And of course, LiBCM can measure the amount of current going into the battery, so you don't even have to tell it what grid charger you have installed. LiBCM can go through and say, hey, I'm putting 1 amp or 2 amps into that battery, and the intake temperature is 140 degrees Fahrenheit, whatever it is, whatever, it's up to 60, 65, 70 C or whatever. Anyway, this will be the new triac stage, and it's a slightly beefier triac. So I was using a D-pack triac, that's a D-pack is just a mechanical size. So that was what I was using. And now I'm using D2 pack, which is a much larger package. And there's actually a D3 pack as well, but that's really wonky big. So you can see here's my D2 pack guy there. And this heatsink actually doesn't contact the D2 pack part. It's just a surface mount part. And then this is just on the copper next to it. So anyway, that's why I tried to test that on there. I think that'll look pretty cool. That'll basically be on the RevD PCB. That heatsink will be up here. So it'll look something like this or whatever. I of course had to move a bunch of parts down and whatnot. So anyway, that was kind of the large thing that I've been working on, is just the thermal performance of the grid charger. Because again, that's the only major difference between the PCBs, between the open beta and the production PCBs. The second thing that I did is I increased the blocking diode on the DC side. This basically is a safety element that keeps the grid charger from being energized when the battery is on. The grid charger is both leaky, so the grid charger, if you actually put the HVDC bus, if you just connect it directly to the grid charger, over here, if you hook the grid charger directly up to the HVDC bus, then this actually uses 10 times more power than LiBCM does when it's unpowered, and that's just because of the feedback circuit in the grid chargers. And both of the grid chargers actually have that behavior. Now they're both, it's a standard LED driver, so they probably use a pretty similar topology. So anyway, what do? You add a blocking diode, and that's exactly what I've done. On RevC, so again, the open beta, there was a very small diode up here, and that handles the grid charger that comes with LiBCM open beta just fine. But when you were putting almost 5 times more current through it, of course that made it quite a bit warmer. So what I did is I actually moved a diode over here so I could have big heat ground planes come out, and of course still keep my galvanic isolation. So that is basically this circuit. So I was doing a 4-wire test so that I could basically push current through and then measure the voltage. So I wasn't measuring the voltage drop in the leads. And so that is our new diode, which can handle that. And diodes also, well, I didn't say that. Earlier I mentioned MOSFETs have a positive temperature coefficient. Well, the triac that we ended up using here, triacs have a negative temperature coefficient. So the hotter they get, the lower their resistance becomes. So for example, at room temperature, this is pushing somewhere around 100 degrees Celsius or whatever, which is totally fine. The part's rated for much more than that. It's rated to 150. And if you increase that from room temperature, 23 degrees Celsius, to like 65 degrees Celsius, which is a 42 degree temperature increase, the temperature on that heatsink is only increasing by, I don't know, I think it's 20 degrees. So anyway, that's the negative temp coefficient, where the more temperature this thing gets on it, the lower the RDS on is. Now, of course, triacs don't have RDS on. It's actually a V RMS thing or whatever. But the important thing is that triacs have a negative temperature coefficient. I'm probably not exactly phrasing that correctly. It's really the resistance has a negative temperature coefficient to it. Anyway, diodes are the same way. The warmer the diode gets, the more the voltage will drop. So this is like a 0.7 volt. Most people know like the 0.7 volts. This diode, the more current you're pushing through it, the lower that voltage becomes as a function of current. So if you're pushing 2 amps at 23 degrees C or whatever, this might be, I don't know, 80 degrees Celsius. And if you're pushing the same 2 amps at 50 degrees warmer, this is only going to maybe get 20-25 degrees warmer. So anyway, I've tested that all pretty well now, and the big kicker is that I'm doing all of this testing with 0 airflow. Of course, LiBCM has fans, but the fans aren't really situated where you would want them to cool off this equipment. This stuff's all going to be up here, and so there is airflow, but when you put the cover on, the airflow is it's not laminar airflow, that is for sure. It's just kind of this chaotic airflow. The laminar airflow is, of course, going axially through the fans, and so there's just incidental airflow here. Now, it is good airflow, but in my testing here, I'm doing 0 airflow, worst case. I'm also doing the worst case input voltage, which on this specific grid charger, the worst case input voltage is actually 110 volts. Because if you drop below that, this will actually start proportionally dropping the output current. And as I mentioned earlier, speaking of dropping the output current, all of the grid chargers that I officially support with LiBCM support variable output current. So LiBCM can adjust the output current as needed. So say you're in Phoenix, Arizona, and it is really, really hot, and you parked at the airport, and somehow the IMA battery is getting up to like 80 degrees Celsius, which I don't recommend. LiBCM is going to know that. It's going to be able to measure the intake air and say, okay, at 80 degrees Celsius, I can only charge at 1 amp, 1.5 amps, whatever that is, whatever that value is. Anyway, that's kind of what I've been working on, is just kind of making sure that this isn't going to overheat. Yeah, so that's it. I'm going to actually order, the PCB is finished. I was waiting for these parts to come in today, and kind of this bag of heat sinks here, alternate heat sinks and whatnot. And anyway, that came in. I just finished my testing up, gathered all my data, and yeah, so as always, thank you for watching. Yeah,